for a Disney version of the solar system for coming in as planets that are immediately coming out dramatically and other. Wouldn't really be quite like this, but you can see that the surface is pretty different. That's Mars going by right now. Of course, the Earth. Now here's the twin planet Venus, but it doesn't look anything like Earth, which basically is because it's much closer to the Sun, with Mercury and the Sun. Short but sweet. If you want to, that's the freebie tour. If you want the tour with Perkins, that's just a freebie tour. Okay. All right, so let's see. What we have here is the capability to observe different parts of the solar system. Now, this is kind of nice because we're seeing kind of those laws in action here. Of course, you see that the period is shorter for a commuter planet like Mercury. You can notice that Mercury does have the eccentric orbit. Venus there, and the Earth have quite circular orbits, as does Mars. So this is the inner solar system that we're looking at here. And you also, by the way, you can tell when we're going to get retrograde motion of Mars, because it's going to happen when the Earth catches up to Mars' orbit. So we would see retrograde motion right about now, as Earth passes by Mars. See that retrograde motion. Now we can also look at some other features here. The asteroid belt out beyond Mars. Things speeded up because we've set things up so that the orbit of Jupiter is too fast. So we see Jupiter there, the swarm of asteroids between Jupiter and Mars. That's the belt that we saw when we looked at that static figure from the book. Now if we go to the outer solar system, looking at Neptune, Jupiter, etc., you don't even see the inner solar system. You're not going to see it because it's so tiny on the scale of the outer solar system. We can go even farther out. Well, actually, this is about the same distance, but we're picking up something called the Kuiper belt, which is a zone where comets reside much of the time. So these are icy fragments in the early solar system that are orbiting out around the distance of Neptune, roughly. These are comets which sometimes become short-period comets and fall in, but most of the time they orbit almost really in this donut-shaped region called the Kuiper belt. But we do have some comets that actually come into the inner solar system. So now we're looking at the inner solar system again. There's Mars. And sometimes comets from the Kuiper belt and a region that's even farther out called the Oort cloud get perturbed by each other and fall into the inner solar system. And when they get close to the sun, they melt and form these icy tails. The tails always point away from the sun, so they don't always lag behind the comet. They can actually be in front of the comet's motion. They always point away from the sun due to the pressure of the solar wind. So we're going to be talking about all these different things as we work our way through our discussion of the solar system and different objects in it. Okay, so we see different types of properties here. We see some regularity already to start out with in that the orbits are all pretty much in the same plane. But there's exceptions. Mercury's orbit is tilted by about 7 degrees. Pluto's orbit is tilted by about 17 degrees. So you can again see this spot right here. Most of the planet orbits are near perfect circles. The exceptions mainly, again, being Mercury and Pluto, which have more eccentric orbits than average. And remember, the eccentricity determines how far circular the orbit actually is. And again, just the idea of the eccentricity. If we want to form an ellipse, we do this with a pencil and two thumbtacks and a string. And if we trace that around, we're going to get an ellipse. Again, just a reminder, the semi-major axis that we talked about is half the long distance across the ellipse. And what we find is that the perihelion distance closest to the sun is the semi-major axis times 1 minus the eccentricity, and the aphelion distance, which is the maximum distance from the sun, is the semi-major axis times 1 plus the eccentricity. So, just to remind you quickly, if the eccentricity were 0, then these little e's are 0. We just get A here and we get A here, which means that there's no change in the distance. It's just perfectly circular orbit. So if the eccentricity is 0, you get perfectly circular orbit. Earth's eccentricity is less than 1%. So Earth's orbit is pretty darn circular. When we look at Mercury and Pluto, we start seeing eccentricities on the order of 10% or so. When we look at comets come in with very eccentric orbits. away from the sun, they come in and they have a much smaller perihelion distance than they do the axial distance. The comets have eccentricities greater than 90%. So that's basically the primary number that's going to tell you what the shape is actually going to be. The orbit. Okay, so just writing down a couple of formulas. I already mentioned the perihelion distance is the semi-major axis times the minus eccentricity. The aphelion distance is the semi-major axis times plus the eccentricity. Now, one interesting thing is if you take these two numbers and you add them, you take the average, you just add them, and you take the mathematical average, you add them divided by 2. What you find is that something's going to cancel. So you have a minus epsilon times A here, and you have a positive epsilon times A there. So if you just add R min and R max, the epsilon parts are actually going to cancel out. And what we find is that A is simply half the sum of the perihelion and aphelion distance. So if you just take the closest distance and the farthest distance, you add them up and you average, that's actually the semi-major axis. So it's just the average distance. And again, Mercury and Pluto has the most eccentric or elliptical orbits with eccentricities over 20% in both cases. Now this is going to result in quite a change in the amount of solar illumination on these two objects, because as we'll see, the amount of solar illumination drops as 1 over the distance from the sun squared. So if you have a 20% variation in distance, which we do, if you look at what's going on here, you're going to get like a 40%, roughly 40% variation in the amount of solar radiation. So temperatures on Pluto and Mercury are going to vary a lot more during their year than we're going to see for the planets that have more circular orbits. This is a table that I'm going to pop up every once in a while here because it summarizes a lot of the important data for the entire solar system. And I do encourage you to memorize this entire table. Occasionally I have students resort to tattoos, but that's not allowed. That's cheating if we tattoo during an exam. So I wouldn't do that. But again, we're kidding about memorizing this first. But here we have our planets. Pluto still is an honorary presence on the list, even though technically you might have heard it's been demoted. It's not a planet anymore. But it is appealing its case, but never told them that. But anyway, no that's all Pluto. So Pluto still has an honorary appearance on our list. The first column here gives us the distance of the object from the sun. So the distance from the sun to the sun is of course 0. So we start with 0. The units here are astronomical units, which are the distance from the Earth to the sun. So we see that the Earth's distance is 1 of these units, 1 astronomical unit. When we look at Venus, it's only about 72% of the distance from the sun to the Earth. So Venus is 30% closer to the Earth. Look at Mercury. Mercury is only 40% of the distance that we are from the sun. So it's going to, of course, be much hotter on Mercury. It's also much hotter on Venus. And that's the main reason that, despite the fact that Venus is a near twin of Earth in terms of mass and radius, which we see in this column here, we see the radius expressed in Earth units. Venus is 95% of Earth's radius, 89% of Earth's mass. If you look at Mars, Mars is only half Earth's radius and only 11% of Earth's mass. So Mars is not a twin planet of the Earth. But Venus nearly is. And Venus is probably composed of the same materials that the Earth is composed of. But Venus is a radically different planet, simply because it's a bit closer to the sun. That 30% closer to the sun that Venus is bumps it out of the habitable zone. It's in the furnace zone. No liquid water. Conditions on the surface are so harsh that we would melt lead. We put that on the surface, it's so hot, it would melt that. So we're seeing the difference that it makes when we vary the distance from the sun. Now going out, Mars is about 50% farther away from the sun than the Earth is. Doesn't seem like a big deal, but that 50% extra distance actually again puts Mars outside the habitable zone. In this case, it's too cold. We don't have a liquid water cycle on Mars these days because it's just too cold on Mars. So again, we're seeing kind of a graphic depiction of this habitable zone idea. Now, as we move out beyond Mars, we start seeing a couple of dramatic things happen. First of all, the planets start getting a lot spaced out, we see Jupiter 5.2 astronomical units out, so more than 5 times the distance from the sun. Now the radiation intensity drops as 1 over the distance squared. So out where Jupiter is, we're talking 1/25th the amount of solar radiation. So Jupiter's getting really quite cold out there. The effect is even more dramatic when we start talking about Saturn, 10 times farther out, about 100 times less solar radiation. And look how far we get out with Pluto, 40 astronomical units out. Now, we haven't really talked too much about this yet, but the distance that the Earth is from the Sun, 150 million kilometers, is large enough that the light travel time from the Sun is about 8 minutes. So when we look at the Sun, we're actually seeing the Sun as it was 8 minutes ago. If the Sun completely disappeared, we wouldn't even know for 8 minutes. Everybody would be celebrating and partying and doing all the things that we like to do, and then boom, it's all over. When we find out, oh, the Sun's gone. Yeah? Well, if you look out into the outer solar system, 40 astronomical units out. So the light travel time is about 8 minutes per astronomical unit. So we're talking about 320 minutes of light travel time to get from the Sun to Pluto. So that's over 5 hours of actual time. So if Pluto disappeared, we wouldn't know for 5 hours. Or if the Sun disappeared and you happened to be vacationing on Pluto, you wouldn't know for 5 hours. All right. We also see, again, that these are gigantic planets. As we move out to the outer solar system, more than 10 times the size of Earth. And we look at, and more than 300 times the mass of Earth. And the rest of the outer planets are also gigantic. Now, the other really telling number is this final column, the density. Because when we look at the density, what we see is that the nearby planets have densities of about between 5 and 6 grams per cubic centimeter, which is sort of the density of a pretty dense rock of some sort on Earth. So these are what we call the terrestrial planets. They're rocky planets. They have a density that's similar to the density of a rock. When we move to Jupiter and beyond, we see the density plummet down to around 1 gram per cubic centimeter. So we're really seeing a different kind of planet out there. As it turns out, we're seeing planets in the outer solar system that are gaseous in composition as opposed to being rocky in composition like the terrestrial. All right, so this is the point I just made a moment ago. With the astronomical unit being about 150 million kilometers, the light travel time from Earth to the Sun is about 8 minutes. And if we think about Pluto, 40 astronomical units out, we get this value of about 320 minutes for light to reach out to Pluto. Like I say, right here. Now, that seems like a lot, 320 minutes. Now, at the speed that light moves, which is 186,000 miles per second, 320 minutes, I mean, is enough time to obviously cover a vast distance. And yet, the distance to Pluto is still only about 1,000th of the distance to the nearest star, because the stars are not 320 minutes away, they're years away from the light travel. That's how incredibly vastly spaced out stars are. We have stars very, very isolated from each other by empty space. An incredible amount of empty space until we get to the next star. So the distance to the next star, our solar system is virtually, well, pretty darn difficult to detect because it's so tightly tied to our own star, the Sun. Okay, this is actually another composite. Actually, this isn't a composite. This was made at one of the last family gatherings or picnic or something like that. And the planets were all together. And we know now that each planet, again, is unique. They also have opinions about things. You know, I have a little silly blue stuff here. The Sun is burning it. This is one of my favorites, which is the rings are bumping into that planet right